Exercise 5.15 says, let XD be a metric space and assume that A is a subset of X. Prove that point X is in the closure of A, if and only if there exists a sequence in A converging to X, which sounds reasonable enough. Not necessarily true for general topological spaces, but true for metric spaces. Up top here, I've copied a couple definitions in a theorem from chapter 2. Limit point closure is the union of A with a set of limit points, and convergence of sequences. So we'll need to use all of that stuff. Okay, so it's an if and only if, so let's prove the forwards direction. So, all right, we are assuming that X is in the closure of A. Okay, well, then that means either X is in A or it's a limit point of A. So first of all, if X is in A, then, okay, we're trying to find a sequence in A that converges to X, and we can pick a really boring one. X, 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 and so on. It certainly converges to X, and if X is in A, then the sequence is in A too. Okay, so why does this converge to X? Let's just make sure we can prove that. Well, we need to find a positive integer n, for any neighborhood U of X that's given to us, such that eventually, starting at the nth term, this sequence is in that neighborhood. Okay. Well, look, this sequence is going to be, every term of this sequence is going to be in any neighborhood containing X. And so we could say, given any neighborhood U of X, let capital N equal 1. Okay. The entire sequence will be in U. All right, that takes care of the case when X is actually in A. What about if X is not in A? Well, then it must be, instead of the closure, it must be a limit point of A. By theorem 2.8. And so, similar to exercise 2.20, which I remind you dealt with the specific case of the metric space Rn in the standard topology. For each n in the positive integers, we have a neighborhood B with respect to the metric D centered at X of radius 1 over n. That neighborhood of X contains some element X sub n in A. Right, because it's a limit point, so every neighborhood of X has to contain some element of A. And all right, so in this way, well, we have all these X sub n's, right? One for every positive integer, so we have a sequence of them. So we define a sequence X sub n in the set A. Okay, well, we have to show that that sequence converges to X. That's our goal. So Now we must show that this sequence x sub n converges to x. All right, well, we got the definition of convergence of a sequence right here. Got to take a neighborhood u of x, given any neighborhood u of this point x, there exists. Okay, well, it's a neighborhood, so it's an open set. And in this metric topology, that means there's a basis element, in particular an open ball, containing x and contained in u. So there exists some epsilon, greater than 0, of course, such that b sub d, centered at x, radius epsilon, is a subset of u. All right. Well, now, if I just make sure that 1 over n is smaller than epsilon, then I actually have one of these neighborhoods up here contained in this open ball and therefore contained in u, right? So let's choose a capital N to be positive integer so that 1 divided by n is less than or equal to epsilon. And then whenever we have n, little n greater than or equal to that capital N, that will imply that 1 over little n is less than or equal to 1 over capital N, which we've chosen to be less than or equal to epsilon. And so we've got x sub n. From the previous paragraph, we have x sub n contained in the ball centered at x of radius 1 over little n. And since 1 over little n is less than or equal to epsilon, that is the subset of the ball centered at x of radius epsilon, which we were given is the subset of u. So, well, we've done it, right? We have found capital N such that starting at that term in the sequence, every term is contained in this neighborhood u of x. Therefore, the sequence of x sub n converges to x. All right, so that finishes the forward direction. Now we got to prove the backward direction. So this time we're going to assume that we have a sequence converging to x. I give it a name. Assume the sequence x sub n in set A converges to this point x. Okay. And we got to prove that x is in the closure of A. Well, let's dispense with the case when x is in A first. If it's in A, then, well, A is the subset of its closure, so then certainly x is in closure of A. And we're done. So, well, how about if x is not in A? Well, then, well, I want to prove that x is a limit point of A. So for that, we want to take any neighborhood u of our point x, and well, by the convergence assumption, what there exists capital N in positive integers such that, well, all I need is that, in particular, x sub capital N is contained in U. Okay. It's also true for any little n greater than or equal to capital N, but one of them is enough. Okay, well, this entire sequence we said is contained in A, so in particular since x sub capital N is in A, Well, we took any neighborhood of X and we've found an element of A which is contained in there, which is not equal to X, since X is not even an A itself. All right, that proves that X is a limit point of A, and so X is in the closure of A. Okay. So we assumed that we had a sequence in A converging to X, and if X is an A, it's in the closure, and if X is not an A, we've also proven that it's in the closure. So we're done.